you for joining us. For everyone watching, we are going to have an interview with Anil Ananthaswamy, the author of the book Why Machine Learn, if I that's correctly, The Elegant Math Behind Modern AI. It's a very lovely book that really give an introduction to modern machine learning from really starting from almost from zero, just from the linear algebra, and from it was quite refreshing. That doesn't assume that much background. And yeah, I read it with great pleasure. Of course, I wasn't really the target audience, I feel, because I already knew a lot of these things, but it was very nice to refocus on it and also to listen to all the historical background that actually I was quite less familiar with some of it. And I really want to discuss it later on. And by reading it, it also felt a bit as also as a kind of personal journey from your side. I felt that in some way you were learning as you were writing it. So that's one of the reasons why it feels so exciting. So was I kind of correct in my intuition, or you really started with all the knowledge and you kind of gave that impression?
Yes. Well, firstly, thank you for having me on your podcast, your show. It's a pleasure to be here. You're spot on with your intuition. That's exactly how it began. So, I used to be an engineer before I became a journalist. So I used to be a computer software engineer, computer engineer. I've done my bachelor's in electronics and master's in EE. And and once I became a journalist, I used to write mainly about physics and neuroscience and things that had nothing to do with technology, because I was wanting to get away from technology and write about basic sciences. And when I would write about physics and particle physics or cosmology or anything in neuroscience, I never really felt like I could do those things. I was quite happy to talk to the researchers, understand as much as I could, and then write about it for my audience. But when I started encountering more and more stories about machine learning, and when I would talk to the researchers about machine learning, I think it was the software engineer part of me just kind of got very excited about it. Because suddenly here was something that not only did I understand to a certain extent, but I felt like I could do this. I could actually sort of learn and maybe get my hands dirty and start doing some coding and things like that. So that's how it began. I got a fellowship at MIT in 2019. This is a journalism fellowship called the Knight Journalism Fellowship.
Okay.
And as part of the fellowship, you can literally do anything you want for a year. You have access to
That's
all
very
the
cool.
courses. Yeah, you have all the access to all the courses in MIT and Harvard, and you have to do a project. And as part of the project, I decided to teach myself deep learning. And it had been 20 years since I had done any coding. So I had to go back to school, literally. I was sitting in their introductory Python classes and learning Python and PyTorch. And so I ended up building a very, very simple, deep neural net to try and uh, predict the future positions of planets. I was trying to see if deep nets could do what Kepler did. It was very rudimentary. I think, if for someone who knows deep learning and that level of coding, they could have done that in half an hour. It took me 3 months to figure it out. But nonetheless, I ended up, coding simple LSTMs and things like that. And I got very excited about the whole thing. And but even then, it was still just messing around with code. It wasn't, I wasn't really understanding the basics. And then I started getting into the math of machine learning, trying to figure out, okay, what is going on here? And it was while I was learning about the math of machine learning that I realized that there were stories here to be told. So your intuition is very spot on, that I was kind of writing about this whole topic as someone who was learning along the way. And hopefully that, like you said, hopefully that excitement shows, because it was very exciting for me to be learning this stuff. And I think for a writer, being able to share that excitement is part of the fun. And I think what makes writing work, when the reader encounters it and they can see that same sentiment coming across, So yeah, I think you're absolutely right that, it was in some sense a very selfish book to write. I said, I want to learn the mathematics of machine learning, so why don't I write a book about it? I think you professors do the same thing, don't you? Like you feel like,
Mm.
oh, I want to
Yeah,
learn something.
definitely.
I'm gonna teach that course, and then you learn.
There is famously was like Weinberg who decided to write a book on general relativity because he didn't know anything about the subject.
Oh well, it's great to be put in the same. No, no, he's amazing. I had the chance to meet Weinberg when I wrote my
Really?
first book.
Oh,
Yeah,
that's
when
amazing.
I did my first book, The Edge of Physics, I had gone to meet him in Austin. Oh my God, he was some presence. I remember not understanding almost anything he said during the interview, and I just barely kept up with him in terms of being able to ask the questions I wanted without really, understanding much of what he was saying. And then I was living in London at the time, and I came back to London, and I would listen to the interview over and over again, trying to figure out what he was talking about. And I realized that he could speak in sentences that were, 15 subclauses long, and you realize that the first subclause and the 15th subclause were completely related. He was able to keep that entire structure of that sentence in mind, so that at the very end, many, seconds later, he's still connecting up to the first thought of that sentence. It was amazing. Yeah.
No, that,
Intimidating
that, that
fellow.
that's a cool story. So you have a lot of this background in physics, and you met a lot of these great physicists. So how did you felt about the transition between passing from like the hard science and moving to like studying some machine learning? Specifically, I really like that you kind of focus on the topic of elegance because I think you have a bit of a different take than many people. There are a lot of people who say there is no elegance in machine learning. It's just kind of messy coding or something like that. And I really like your kind of take. No, that is not true. Maybe you don't have the most complex quantum field theory, but I think there is a lot of fundamental elegance there, and I think you get that message across. But how did you decide on the kind of main focus of elegance of the math instead of, for example, just focusing on the complexity of the coding or stuff like that?
I That might be just my uh, predisposition. I think and it's something that I've always had when I have tried to write about a complex subject. The way I've approached it is I wanted to understand it at the very basic level and see if I can distill the principles in order to write about it. And oftentimes, when you get down to the basic principles, there is elegance there, and it's quite beautiful. It's the complexity and the craziness only comes much later when people are trying to build things. But at the very, like when you look at the perceptron convergence proof, right? Um, in fact, that proof was the proof that made me want to write this book, right? I mean, I
Where
was
everything
looking,
started, right?
yeah,
Essentially,
exactly. Exactly. And you look at that proof and it's just very simple linear algebra and it's proving something quite profound, especially for its time in the late 1950s, early 1960s. And that proof was what made me feel like, okay, I just need to go looking for these kinds of things in machine learning that would help me make a story about the math. So I kept digging and I like, for instance, kernel methods and support vector machines, I think they're amazing. PCA. I mean, it's such a simple thing, but you kind of when you grasp it, it seems so magical. And there were lots of things like that. I think, I mean, even backprop, which is kind of not, you know, dismissed now as, oh, okay, it's just a simple, application of the chain rule. Well, yes, but it's also pretty beautiful. Like the fact
mm,
that you can, do something with one hidden neuron and the algorithm that does it for one hidden neuron is the same as the one that does it for God knows, 100, 200 hidden layers.
mm.
It's the same algorithm, and I find those kinds of things amazing. Of course, elegance is subjective. Like you said, a lot of people will disagree about the elegance of. In fact, I got those comments like, people would say, "Oh, what's so elegant about linear algebra?" I said, "I don't know. I mean, it just feels like very elegant to me." And now you're seeing it, right? People are waking up to the fact that all of this energy consumption that's going on for building large language models, 50 to 90% of it is matrix multiplications. So how, the idea that you have to focus on this particular operation to make your AI systems more efficient, at least the way they are architected now, uh, brings the focus back onto the math.
And yeah, that is very interesting. There is so much meta narrative in the current discussion, right? Which you actually need to know a lot of history to know where it comes from, right? For example, a lot of people will say deep learning is a black box. Okay,
Mm.
where does the statement come from? It comes from a criticism that people in like statistical learning theory, for example, or in symbolic AI will raise at deep learning. Uh, it is not very obvious to me that out of context it means something for the general audience, because a car is a black box as well. You usually don't understand how the engine of your car works,
Right. Right.
um, so that's also what I really appreciate in your book, that you give a bit the origin of these different philosophies. Some of them ended up actually like contributing to the what is modern mainstream, and some of them kind of a bit left behind, still kind of a bit in the literature. Uh, one interesting things of your book is that you spend quite a lot of time for methods that are considered a bit out of fashion nowadays. For example, you mentioned kernel machines. Can you explain, is it really the pursuit of elegance, or there are other reasons why you spend so much time on those methods?
I felt like it was, I think, again, an effort to understand the basics. I felt like, I mean, there were multiple things at work when I was making the choices about what to put in. Uh, I definitely was looking for kind of a historical narrative. So, if you started at perceptrons and then you wrote about what happened in the 60s, and then you had to jump all the way to the 80s because that's when, neural networks came back into vogue again. Uh, and if you just miss out what happened through the 60s and 70s, that seems like a big hole, and so much was happening, right? And even after in the 80s, once we had backprop and once we had CNNs, they didn't really take off for a long time. And what was more important at that time was support vector machines and kernel methods for a long time. So some of it was not necessarily about elegance of the math, but just trying to give a complete picture of how we have come to this point in machine learning history, and not make machine learning only about deep learning, because there is so much more to it. And in fact, now you're beginning to see that, okay, even when we talk of deep neural networks and deep learning, the connections to, let's say, kernel methods and kernels are becoming obvious, that there's an equivalence between, for instance, the neural tangent kernel, the infinite width neural network approximates a kernel, and all these things are kind of becoming more obvious now. So I felt like if I had just jumped directly to talk about deep neural networks and deep learning, I think the reader would have missed out on this whole amazing intermediate history. Uh, Possibly also that I wanted to talk about things, like the role of probability and statistics. I felt
Mm.
like without explaining what a Bayes optimal classifier is, or what it means to estimate probability distributions, I don't think you can grasp the importance of generative AI. And if you start simply with simple examples, then you can kind of start understanding what today's big networks are doing.
Yeah, and yeah, that's very interesting, and I do feel it's a bit of a problem nowadays in our field, that young people just jump immediately on LLMs, and I mean nowadays I feel very old, because already I just talk to students, say, oh yeah, it's a convolutional network, and they don't really know what it is. It's even
Yeah.
most of the deep learning revolution. So it's I do feel that your book is also very useful for people that maybe they are AI researchers, but they actually went straight to the meat,
Mm.
and indeed they're missing a lot of things that can be useful, and can be useful even for studying deep learning, as you said, like kernel method can be used for studying deep learning, right?
Yeah.
Um, uh, so I find very interesting this a bit of entanglements with the history of the subject. First of all, it's a field where people have been quite very opinionated, and there have been quite very strong controversies, right?
Mm.
Um, and it's nice to see that things essentially started with the perceptual learning group, in the sense that started the essentially the neural network literature, right? There were McCulloch
Mm,
bits before, but there wasn't a learning rule.
mm,
But then it also started machine learning as a whole, right? And also started the idea of rigorous proof, convergence results. So essentially everything that is machine learning.
mm.
Uh, I'm ignoring symbolics, but I will say that those symbolics, they wouldn't call themselves machine learning anyway.
Yeah,
Everything started from there. And then there's been this divergence of people who really cared about the math and people
mm,
who didn't, you know?
yeah,
And then we
yeah.
go back to this point of elegance. And we saw historically that the faction that essentially did not care about the elegance of the math ended up winning. So is it a bit of a cautionary tale that maybe we should be careful about being too much attracted by elegance? Uh,
Um, yeah, I think this plays out in physics also, right? I mean, this debate is playing out in theoretical physics even now. That this focus on the elegance of theories may be leading, particle physics or people who are doing fundamental physics. They might be going astray because of the focus on elegance. Like when you think about theories of supersymmetry or the elegance of string theory, and supersymmetry still we don't have any sign of it, despite all the claims about its elegance. And now the space in which supersymmetry might exist has been pushed to a corner of parameter space which doesn't look very elegant, but it might be. That's where you might find it. So yeah, this debate is going on in physics also about how much focus one should place on elegance. I don't have any particular. I don't know whether there is anything fundamentally sound about pursuing elegance. I mean, I just see it, and if I like it, I call it elegant and write about it. As a scientific method, like should you only pursue elegance? That I would imagine is a personal taste. Some researchers are going to like doing that because that inspires them. For others, it's a hindrance. And finally, if empirical data and your theories start merging, that is where we should be going. And looks like that's what's it's coming around now, right? We have so much empirical data now with deep learning, and we don't have the necessary theories, mathematical principles to explain all the various things that we're observing. And we're beginning to realize that, for instance, this whole issue of sort of over parameterization of deep neural networks and why they're still able to generalize, etc. And the fact that standard statistical machine learning theory doesn't explain that. We're beginning to see that there was already evidence of that with kernel methods, but people
mm,
ignored it, right? Because everything in the standard regime was so nicely explained by the existing theories. Um, so the anomalies were kind of pushed aside. But now deep neural networks have basically become the face of those anomalies, right? They're forcing us to consider the fact that, okay, maybe the theory is not complete. So it seems like a nice interplay between empirical stuff and theory. In the way I feel, both have to go hand in hand. You can't have one without the other.
mm. Yeah. I feel as well. I mean, we're really trying here to. I mean, the field is becoming quite atheoretical. What I find a bit that there is a bit of a missed opportunity, which I guess is good for us because there is space, is
Yeah.
that there has been a kind of insulation of the theorist. So nowadays there are people who are practical that they will rarely touch any theory, and there are
Mm,
theorists that they will rarely touch any practice.
mm,
And as you said, it was kind of in the past as well. I mean, you had that very funny story of the creators of kernel methods, right? That they were submitting a paper to Colt,
yeah.
and they say, "Oh, it's nice to have an application paper for us."
Yeah, yeah, yeah.
So
And the
it
people submitting it, Isabel Guion and Bernard Boser, thought that was the best theory that they could have done. And the
yeah.
conference organizers thought, oh, okay, we'll have an application paper. Yeah. Yeah.
Well, I do feel, what I say people that I think we need a bit more physics in machine learning because I feel people all want to be mathematician, but mathematics came after usually, or at least mathematics like people do it nowadays. Because back in the days, mathematicians didn't care about rigor, right?
Yeah.
They were before. There were most of interesting results of calculus came before people even knew how to make it rigorous, and it was fine for everybody. But now mathematicians want to make rigorous things rigorous from day one. And I think what is really missing a bit in the field is just using math, but without really wanting to be computer rigorous. And I mean, as you know, by of the your interview done with physics, right? That is, if that was our criteria for physics, we would still be to textbook
Yeah,
quantum mechanics because we wouldn't have moved to quantum field theory at all.
yeah, yeah.
Um,
It's yeah, it's very timely that you say this because just yesterday I gave a talk here in Bangalore about how physics principles have inspired generative AI. And so in order to put that talk together, I kind of went back to looking at how, things have come about. So looking at Boltzmann machines and Helmholtz machines. Um, and it's very, very interesting to see how much physics has played a role. Uh, and in a way, there's a very nice talk that Jeff Hinton was giving after his Nobel, where he was explaining to his audience an artificial neuron, and he said, "Oh, but this is a very simplified version of the biological neuron." So I'm just paraphrasing here. He was pointing out that the model is an extremely simple version of the biological neuron. And then he says, "Oh, in that sense, I'm a physicist. I ignore the complexity." As- So, but then ignoring that leads us to this place, right, where we can come up with pretty amazing things. And then if you look at in the course of the evolution of the Gen AI models, there's been, especially with the whole idea of minimizing variational free energy, and that seems like a very staunch principle now that seems to be not just there in machine learning, but it's a very big part of cognitive neuroscience.
mm.
In how we think the brain might be doing a lot of these things. And then, of course, diffusion models, which are so obviously inspired by physics. And it's very beautiful. I agree with you. I think physics should play a big role. In fact, somebody in the audience yesterday asked about where do you think the next inspirations from physics would come from? And I uh, I was thinking that maybe this whole idea of variational free energy minimization is already a kind of overarching principle. And so the next inspirations might come from neuroscience, where they're actually seeing how the brain might pull this off, right? And maybe trying to figure out how to architect AI models based on our growing understanding of what the brain might be doing.
That's also been quite controversial in AI with fluctuations, right? Like neural network theory starts from neuroscience. Like the original neural network theories were all unapologetically trying to mimic the brain. And
Yeah.
then at some point, like it was like in the 90s, people got, oh, but we have statistics. Actually, this all neuroscience is nonsense. We are not we are not soft sciences. We're just doing statistics. This is
Mm.
just gradient descent and so on. Which I mean, it is true, but you wouldn't be there without neuroscience, so it feels a bit disingenuous. It is true that you can remove it. You don't need to interpret it in terms of neuroscience, but neuroscientists discovered it
Yeah.
throughout. So, but then I did experience in the field that there has been like tendency to say, okay, like we don't really need neuroscience, right? Or it's as if we're trying to build airplanes by looking at birds. That's the
Yeah. Yeah.
um,
And
so.
that seems fine too, right? I mean, every field has a launching pad, and it might have been inspired by something, but then the subsequent researchers are so far away from the point of inspiration that they look at the whole field as completely separate,
Mm.
and they are able to advance because of that also. So not being held back by where the field started, but moving in it. Like what deep learning research is doing now is quite far away from where neuroscience, inspiration began. So that also is helpful, it seems like. But I
Mm.
agree with you. I think acknowledging the inspiration from neuroscience, cognitive neuroscience, physics, all of that is so important. I think for me that was probably the fun part of writing about the book because I don't have to worry about being siloed in any one particular
Mm.
discipline. As a writer, I was much more interested in the connections between all these ideas and fields, and the more there were to discover, the more the story became nice and complex, and so it was always exciting to find connections between physics or between neuroscience and and machine learning. So yeah, that for me it just feels like one big giant thing that is all interconnected.
So one of this main kind of historical point about the neural network theory is the invention of backpropagation, of the discovery of backpropagation, and it's a very interesting story that I feel is I think you outline it very well in the book. But for me, there are some things that I don't understand very well, and I think actually in your book you gave me a good key of understanding, because one of the things is that if you think about neural networks and you have any understanding of mathematics, you should probably arrive at that quite quickly, right? In the sense, it's the obvious thing to do. And those were
Mm,
very smart people. We're not talking about people that were not smart.
mm, mm,
Um, and I think what you point out in the book, that they were using discrete activation functions, of course, in the perceptron.
mm.
And that seems to be actually a big driver of the fact why they didn't do it, which is, it sounds quite funny, like,
Yeah,
because,
I mean, it just seems in retrospect, it seems like why didn't they think of, changing that activation function from a, threshold function to a sigmoid or something. Um, yeah, I mean, but again, these are only in retrospect, right? You mentioned symbolic AI earlier, and a lot of the sort of dying down of the neural network research was thanks to some nifty math by Minsky and Papert when they proved that the single layer neural network will not solve the XOR problem. And then they kind of suggested, without any mathematical proof, that multi-layer neural networks will also not solve it. And that seemed to have had such a dampening effect that only maybe, I would imagine like a handful of people were working in neural networks for 15 years. So part of it might just have been the fact that there were just not enough people looking at the problem. And sometimes, that you literally had Hinton and a few others who said, okay, we think Minsky and Papert were wrong, that this is going to work. Uh, but yeah, I agree with you. In retrospect, these were smart people, and Hinton, of course. I mean, he was looking at it from the late 60s onwards. It took him quite a while to come to the point where they could figure out backprop. And saying that backprop as an idea itself was there, right? I mean, it was there in other fields. It was not formulated in a way that was useful for training neural networks, which is what the big contribution of Hinton, Rumelhart, and Williams was in their 86 paper. But the idea of kind of, sort of chaining together derivatives was already there. Um, and they just did a nice job of pulling it all together and then showing that if you use backprop, what a neural network learns are features that exist in the data. Um, but the simple changes that needed to happen, changing a neuron's activation function from something that is not differentiable to something that is differentiable. Yeah, in retrospect, that, seems so simple, but it was amazing that it took so long.
yeah, maybe they really, maybe this was a bit that the elegance of the perceptron learning rule is something that they didn't want to let go of the finite convergence property.
Yeah, and but the other thing that that I wonder, because when you talk of the history of neural networks, everyone brings up the perceptron. Almost no one I talk to brings up the least mean square
Mm.
algorithm
Yeah,
for
that was a
training
yeah.
the single hardware neuron that Bernie Widrow came up with. And I suspect that if if Adeline that Widrow had built had gotten more attention, because that is really the true precursor to backprop, not the
Mm.
perceptron learning algorithm, right? So because Widrow's algorithm is a very noisy stochastic gradient descent. He's got an algebraic version of that. But that's what he's doing in that algorithm, and that was also done in 1959. But somehow, when history looks back, they keep talking about the perceptron, and some of it is just the media hype that surrounded the perceptron. Adeline never got that media hype. Uh,
Mm.
but they're both linear classifiers. They both use linear neurons, and but one is using an algebraic version of gradient descent, and the
Mm.
ideas were there, right? So I wonder whether that's also an historical accident where if the attention had focused on Widrow's LMS algorithm, maybe we would have arrived at backprop earlier.
Yeah, I feel because of course a lot of filtering, and that was a great chapter of the book, by the way, because it's rarely told. So I really enjoyed that story because I actually did not know. I knew, but yeah, I mean, in the 50s, a lot of filtering theories, right? Kalman filtering, and everything was coming in. They're further very connected, and of course, in this case, I didn't know that they basically discovered SGG, so that was very interesting. I don't know if they, again, it's maybe being swayed a bit by elegance because for a mathematician, the linear theory is so beautiful that you are not going to introduce nonlinearity unless you actually have a reason to. And also computation, right? I did not have the efficient. So there you really need to be super efficient. The theory, linear theory is beautiful. You don't need anything else before you're happy, right?
Yeah.
That can be the reason, but indeed everything was there. I feel that the neural network people had more the motivation of actually because in
Yeah.
filtering theory, the problems are actually linear often, right?
Yeah, and there was another thing that Hinton had mentioned when I had interviewed him, and I put this in the book. I don't make a big deal out of it, but it's there in one paragraph somewhere. Um, when Rosenblatt had written about training multilayer neural networks, he had suggested stochasticity as a necessary ingredient in the network. And for a long time, Hinton thought that the stochasticity should be in the neuron. And so his early neural networks were stochastic neurons, and they didn't lend themselves to, obviously, to backprop because of the discontinuity. And it's only Rumelhart, I think, who suggested to him that, the stochasticity doesn't have to be in the neuron's activation. It should be in the way you initialize the weights of the neural network. And that apparently was a big deal. Like, again, all these things in retrospect, right? And so who knows how long it would have taken if not for that one suggestion from Rumelhart.
That's a very good point. That this is very obvious in retrospect, but imagine yourself doing it actually. Yeah,
Yeah,
it
why
is
would you
kind of
think
you
that,
need
right?
to think about. But yeah, let's
Yeah,
start with zero, right? Why am I going to put random mass in my weights?
yeah, yeah.
Uh, so yeah, that is indeed it's a very cool insight that I actually never heard that story before. Um, yeah, so the origin story of neural network is just very interesting. Like, one fact that I find mind blowing is that if you think about Rosenblatt talk in the grand scheme of thing, it was spot on everything. You know,
Yeah.
it wasn't how, right? I mean, yes, it was hype, but just look at where we are now. Was it
Yeah.
hype or it was
Yeah,
completely
I
right?
mean, he was seeing some. I think it was hype only in the sense that what they built was obviously not going to do it, but he saw that this is where it'll go, right? So,
Mhm.
we have ended up in a place that is very close to what was being promised in the late 1950s.
That's
Maybe not,
amazing.
maybe not consciousness yet, but certainly a lot of other things. And then of
I
course
mean,
consciousness
yeah.
also depends on what one's view of consciousness is. So that's another can of worms. But you
Mhm.
know, yeah, it's yeah, I
Yeah.
agree with you. I think Rosenblatt was pretty amazing in that respect.
I don't know if we should get there. I mean, I wanted to ask some question about. I mean, for me, just it's not clear when people talk about consciousness if they, first of all, they don't agree on the definition. So it's just we just having argument because we define things differently. No one is actually a definition of what that actually means.
Yeah,
And even if people, if they have if people who have a definition, it's either untestable. So I don't know if GPT has consciousness, and I don't know if you do have it. So what are we talking about?
yeah,
Or it's not what people mean by consciousness. Oh, it needs to be this sort of time-dependent complexity. Okay, but that's another thing that you invented. But I mean, whether it correspond to my fact of, um, I suppose that people ask you a lot of this kind of questions. I I don't know what's your opinion. I just don't think it's useful. I think there are useful related questions, right? Okay, when we should start treating AI as an object of morality, right? Are we morally responsible if we are mean to ChatGPT? And if you ask me now, I will say probably not, but we are crossing a bit the boundary, which maybe we should start thinking about this topic. I don't, what
I,
is your view?
I yeah, so this has been something that has been not necessarily the question of morality, but the question of related question of consciousness, because has been on my mind ever since I wrote my second book was called The Man Who Wasn't There, and that's an exploration of the neuroscience of the sense of human sense of self.
Oh,
So it was only after I finished writing that book that I started really understanding what philosophers and theologians and neuroscientists are arguing about when it comes to the nature of the self or the nature of consciousness. Uh, and after writing that book, I think I slowly before writing that book, I think I was agnostic about what my position was in terms of things like materialism or functionalism, etc. But now I think I'm firmly a materialist and potentially a functionalist. So and now even more so after writing this machine learning book that I have a more computational view of everything. So if what we are is just an outcome, and I say just in a very, as if it doesn't mean much, but of course we are a very complex thing. So if what we are is an outcome of computational processes, and if the outcome is also independent of the substrate that is carrying out the computation, uh, then I don't see any in principle reason why machines are not going to get there, why we won't be
mhm.
able to build machines, right? So today's GPT, I would agree with you that we would don't yet have to worry about the compute. We don't have to worry about having actually come up with those computational processes that lead us to a place where we can say something is conscious or not conscious. But I don't see any in principle objection to getting there. And if we are going to get there, then we have to worry about the morality of how we treat these machines. It
The
won't be
problem
any
that
different.
it's unknowable, you see, because the only way you can actually know about people is by asking them, right? And if you ask an untrained, the problem that the answer you will get from an LLM is completely the answer that the designer of the LLM wants you. If LLMs are trained on human talk, so if you ask to an unfiltered LLM, it would say, "Of course, I'm conscious. What are you talking about?"
Yeah.
And it's right because it's human, because that's so.
So,
You
so
see.
I'm not thinking necessarily of LLMs as our end game, right? So, and I'm sure you probably also are looking at LLMs as just a stopgap to something that's coming now in the future. I can imagine us building AI systems that learn about their environment from the ground up, rather than this kind of top-down training of LLMs from this huge, vast amount of data. So you can imagine, uh, AI models that are more like children learning about the world from their environment, and you equip them with some sort of uh, quote unquote emotional axes, that allows them to make decisions about what to learn, what feels right, what doesn't feel right. And eventually, if we build it like that, they will potentially have the same mechanisms at work as we do. Uh, and I would agree with you that we would need some sort of theoretical framework that is well accepted for us to make the claim that we can trust. Like, just like when you and I say that we are conscious and we are reporting something, there is still an assumption there that you are the same as me and I'm the same as you, um, and we're using our inner subjective experience to make decisions about others. Um, and when a machine will give you some sort of reply to a question, how do we trust its output? And LLM, I agree with you, I'm not going to trust it. But if we build machines differently, intelligent machines differently, where they are, let's say, embodied agents that are learning about their environment from the ground up, and the representations that they develop in order to reason about the world are grounded in physical reality, and they have some sort of axes on which they decide this is painful, this is not, whatever that might be. I'm using anthropomorphic words here, but you know what I'm saying. Then I feel it will be much harder to deny what they're going to say.
Yeah, but again,
Right.
like you have some assumptions about LLM, right? And of course, this is there is a bit of a divide nowadays,
Yeah.
right? There are what you're saying, for example, I can like from Sutton, I can and Lacan, for example, they have similar opinions.
Mm,
The way I see it is actually more aligned with. I don't think that LLM is the end because obviously
mm,
don't necessarily believe in the end. I
mm.
just don't. I think that we work more like LLM than the ground up people think. I just think that we are more efficient learners. We don't need that amount, but I think
Yeah.
we imitate by a very large amount. And I think if you see what children do, children start speaking before they understand what they say, um, because they just repeat.
True. True, true. That I don't, that I agree with you completely. But at the same time, the nervous system that a child is born with is the outcome of an evolutionary process that has been developed from the ground up by evolution, right? So we possess a brain when we are born that is the outcome of hundreds of millions of years of evolution of nervous systems, and these are nervous systems that have encountered their environment and whatever architectural inductive biases we come with that allows
Mm,
us to be generalized learners as soon as we're born is an outcome of bottom-up processes.
mm, yeah.
So whether we can replicate that in the way we build machines, I have no idea. I know people are trying that, but the yes, I agree with you that once we have this nervous system that we are born with, then we can the way we learn, some of the things do mimic the way LLMs learn, right?
Mm.
But all of that architectural sort of inductive bias that's already there in our brain is a bottom-up affair, right? I mean that
Yeah.
has come about through evolutionary processes. So we are certainly a mix of both, and I wonder whether we're going to, figure out how to build machines that are also going to be part LLM-like learners and part sort of embodied agents that are learning by interactions with their environment.
The fact that you can make embodied LLMs, I'm not sure that embodiment, I feel we fundamentally don't know what is special with us. Because I think
Mhm.
it's obvious. I think if you use an LLM enough, it's obvious that an LLM does not have intelligence that human has. On the other hand, it can answer, it is obviously intelligent. I mean, people, I
Yeah,
mean, again, we can disagree, but people who say that LLMs are not intelligent, I don't know how to relate because I've used them enough. I can answer
yeah,
complex question in an ambiguous way. Will be
yeah,
able to figure out exactly what I'm asking and actually give the solution for something that has never been asked before. So if you
yeah,
don't call that intelligence, we are redefining the word, and then I don't know what you
yeah.
mean by that. You
Yeah,
know? Uh,
again, I agree with you. I think, the fact that LLMs have problems doesn't take away from the fact that they're amazing uh, machines, right? Like today, the things that I can learn by querying an LLM in ways that were just impossible 2 years ago. And there's such a breadth of knowledge, and there's such a breadth of or depth of knowledge also, breadth and depth in a single machine. Uh, I agree with you. I think if you were interacting with a human who had that ability, we would obviously say that human is intelligent, even if the
yeah.
human is making mistakes, right?
Yeah, no,
Which
exactly.
LLM.
And the nice thing is they make mistakes in a quite human way. And that's interesting. And people don't stress it. But if you actually see what, like, if you ask, give math problem, usually the mistakes they will make is not, it's usually they get confused. For example, if there are two concepts that have the same name in two fields, sometimes they
Mm,
would just merge them, which is the kind of mistakes that a student often make, they just
yeah,
think that
yeah,
is the word reference. So
yeah,
I do feel that we think that we are defined by our intelligence, and I think that's where we're wrong. I think LLMs are intelligence, but I don't think that intelligence is what makes us special. I think there is something that is more about being alive than about being intelligence. uh, I feel we're less trapped by intelligence. We can escape it. Do you understand what I mean?
yeah,
Like
yeah.
creativity, like.
Yeah, I mean, but on the other hand, human creativity also, you look at what sort of diffusion models can do, for instance, right? They do navigate some extremely complex spaces, mathematical spaces, and come up with all sorts of things that a human wouldn't be able to. So
Yeah, but
there also, I feel like it's a definitional issue. Like I agree with you. We all feel like we have something more than machines. But if you take a sort of materialist computational view of this whole process, then we're just very, very sophisticated machines. Yes, the machines that we're building are nowhere close, and hence we feel like this huge gap. But I don't know if there's an in principle gap. I think it's
yeah, no,
just
I
a,
don't. Yeah, I
yeah,
mean, it is a possibility, right? I don't think we need to be slaves of our modern philosophical outlook. I think there is a possibility. There is some in principle reason. I mean, as you say, I tend to agree with you, like that. But that regardless whether in principle or not, I do think that is in practice true at the current moment, in spite of the intelligence. And you gave example of diffusion models, but this beautiful creative stuff usually come from a creative prompt. If you would just get to sample unconditionally without a prompt. And it's the same for LLM. LLM can do very creative things, but usually they need to interact with a creative source in order to be creative themselves. So what I've never seen is just creativity without human in the loop at all. Uh,
yeah,
because once you say, I want to see a knight riding a panda on, well, you're right, the creativity is there, and then the diffusion model needs to render it. You know, you supplemented it yourself,
yeah.
and then it will render in a creative way. I'm not saying that the creativity is zero, but it's different from what you expect from a human, right?
Yeah, and I wonder whether this specialness that we feel is a lot of it's tied to our existence. Whereas for LLMs right now, I mean, it's not an existential question whether they're switched off or not, right? I still feel like if we end up building machines that operate with that axis inbuilt in them, where there's some notion of existence, where there are computational models of their selves that are working to preserve their selves somehow, just like we have, right? I mean, so when we think of ourselves, we have bodily selves. So our bodies are going to defend themselves if the integrity of the body is in danger. That's just the nature of the self. We defend the integrity of our cognitive selves, however, inflated that might be, or however small that might be. If something or somebody threatens the notion of what we think we are, we will defend that. And I think our creativity and all of the things that we do as humans is intimately linked to a preservation of the notion of one's self. uh, and people do it differently. And one of the famous phrases about artists is that they are tortured selves. What does that mean? Like,
Mm.
so they're trying to escape their tortured selves through their creativity. So I don't think we have any such torturous things going on in AI right now, right? They are not feeling tortured because we switch them off or
Funny.
because we say bad things about them. But if we do build machines that operate on that axis, or if we figure out ways of uh, imbuing these machines with uh, self models and higher order self models, and uh, then some of these things will come into play, and who knows, then they might take the same route to creativity. Hard to say. I don't know how the future is obviously going to look. I don't think anyone does, but I wouldn't rule it out. I think our creativity may turn out to be nothing terribly special, right? It could be that it's our current way of escaping um, local minima, that our brains are, during normal functioning, where we are feeling trapped in ourselves, from a sort of neuroscientific neural network perspective, that could be just a dynamic system that is trapped in some local minima and it feels awful. And some external energy input, or just some stochastic process, just dumps you out of that local minima into a different part of the space that the brain is navigating, and that feels like creativity. But it could be just a very mechanistic but stochastic process, right? And so who knows? With machines, I don't know whether it's
Except
impossible to build machines like.
the stochasticity is there in machines as well, right? I am actually thinking that we should actually start using true randomness because I feel that pseudo randomness can actually choke them. I mean, from information theory, I do know that there is a limit of creativity you can have if you don't have a source of true randomness. And it's not zero now, right? Because even if they're looking, usually pseudorandom will initialize with something like clock check, which will have some level of stochastic measurements, but it's still much less than the actual nominal bandwidth, you know? If you so and people in the field have developed to say, okay, pseudorandom is indistinguishable from random, but that's true. That we developed this wisdom in regimes that are very different from an LLM and from so whether actually you get the same level of intelligence with pseudo randomness or with randomness, it's a different story that I would like to investigate, and I feel few people are. Although I guess people are starting to get proper like pro randomness chips, so maybe we will see that soon. If yeah, because in general I say it like you that stochasticity is essential. My opinion is that you cannot fake stochasticity. So that's I come like from an information theory point of view, and determinism does not create anything. So stochasticity needs to put from the outside. Otherwise, the deterministic system is completely predictable. But I do feel also, I don't think we have any special. I think we have sources of stochasticity in our brain and outside, which the LLMs have as well, by the way. Even if they don't have stochasticity in themselves or that much, they will have that in outside anyway, and that's functionally equivalent. But yeah, they should be able to. I mean, in practice, I see that there is a big disalignment between their intelligence and their creativity. They are substantially less creative than they are intelligent. So that's something that is interesting to see.
Yeah, I would completely agree with you. The intelligence or the ability for intelligent behavior in a single LLM, I mean, it's just insane right now. It may not be the kind of intelligence that certain researchers think of. It's not obviously it's not embodied intelligence, and it's not intelligence using representations that are grounded in physical reality, etc., etc. And so that does lead you to reasoning in ways that don't necessarily work, but still they're able to accomplish so much, right? And I think so when I think about LLMs as probably not being the end game, it's more to do with the fact that there are some obvious drawbacks that they bring to the table, which is inefficiency for one. They're highly sample inefficient, huge energy consumption. So there's something that the way they are learning is not quite the way we learn, right? I mean, obviously, we do it so much more efficiently. So there's something that's missing. And the fact that there is really no mathematical guarantee of correctness.
Yeah, but
May not, even we don't have that as probably, right?
yeah,
As
exactly.
humans,
So,
yeah,
but maybe
yeah.
it's good that we don't. I feel if we did, we would not be very smart. I feel that's.
Interesting. So
I don't know. I see
that
that
might be
in.
the trade-off, right?
Yeah.
Mm,
Okay. But yeah, this is very interesting. I mean, in inefficiency, people maybe could argue that okay, but that's sure it's more expensive, but doesn't mean that it's qualitatively different. But I suppose you will argue that what makes us efficient also make us more able to think creatively, for example, as far as I understand it, right? So that it's not because is the inefficiency itself the problem? Because I say, okay, but I still have a huge computer, so I should be able to get human level intelligence, right?
mm,
More expensively, but that's not what I
mm.
care. I have a lot of money.
Yeah, I feel like maybe the two are related. The fact that we are such efficient learners and our intelligence has a certain kind of um, efficiency in terms of the amount of power it takes um, is obviously because of the way the brain is architected and whatever algorithms it's using, etc., to do what it does. But the very same internal structures that the brain has and the modeling that it's doing may also be the stuff that's enabling the creativity,
Mm-hmm.
right? Right. One obvious way that seems to make sense to me about why we are sample efficient is maybe we have very, very good world models that we use for running counterfactual simulations, right? So we're not reliant on external data We can do a whole bunch of reasoning without sense input necessarily, because we have sophisticated ways of doing counterfactual thinking about various scenarios, this and that, inside our heads. Now, but that same process could also be the engine for creativity, right? Because that's what's allowing you to explore some sort of state space of concepts that makes it possible both to be energy efficient and sample efficient in terms of how you learn from data, but also gives you all this ability to roam freely, untethered to, sense input.
I feel that LLM have a better word model than us, though. I mean, I guess that I understand that this is controversial, but I think that they can reason and they can know, and they know more things. Um, so
Yeah,
you can argue that it's not physical. I mean, personally, I mean, again, you said that you're a materialist. I tend to be a kind of informationalist.
yeah,
I don't think that matter is particularly special. In fact, if we go deep into physics, everything boils down to information anyway. So I see them as embedded, just not necessarily in a three-dimensional world, but I mean, at the end of the day, we are more embedded. I feel that humans being are more embedded in a linguistic and informational world than in just a physical one. Most of the time, I don't think about my spatial location. I think what my wife told me, and that's just information. That's the same kind of.
Yeah.
But I do feel that they have a good word model. So I'm a bit skeptical about that explanation because I feel I have seen them reasoning and they make counterfactual. And they can definitely be prompted to do it more. So if that was um, because they only hint that a bit of I had, which is a bit unrelated, but I don't know if you think it's connected, is that I feel that can forget more. And that's I feel that they can get trapped in knowing too much, you know? That, I mean, if you think about the way we are creating offerings, because we don't know. If we knew, we wouldn't. If we knew something similar to what we wanted to do, maybe we will not exactly try to do something new. Sometimes I mentioned the story by Borges. Do you know, like the Funes the Memorius?
I've heard. Tell me more about that story.
It's a beautiful story. You should read it.
Oh, it's a long one. Okay, all right. Yeah.
No, it's not.
Mm.
No, it's not long. It's quite short. The idea is that
Oh.
Funes has had the kind of an accident, and at some point he started to remember everything.
Mm.
So and then it completely zero this level of intelligence, because, for example, if he couldn't understand that the dog from one angle could be possibly the same dog from another angle, because those things are clearly different, or it was giving numbers, individual names, because he could remember them, so he didn't need to actually organize. So he kind of didn't need to compress anything, and then kind of all intelligence disappeared from him.
Right.
And this is
Actually,
actually
I
very
mean,
related.
that makes sense, right? I mean, I like the way you phrased it, that, it's because we forget. Another way to think about that is probably saying that we are much more capable of abstracting. Our world models are much more abstract and not as literal as what might be happening in LLMs, right? So then if we have world models that are very abstract and more conceptual, then the algorithmic structures that you need to reason using those abstractions would be very different from the way an LLM works. And so maybe, that's both the reason for our energy efficiency and for the fact that because we reason in abstractions, it comes inbuilt with a certain level of stochasticity, uh, and that's where the creativity also comes from, right? I don't know. This is all sort of speculation
That's
from.
interesting because I mean LLMs are trained mostly on language, so that it may be, as you said, maybe they're a bit too literal because they have never kind of experienced a non-linguistic kind of reasoning.
Yeah.
That maybe sometimes you need. Sometimes just language doesn't read you to the right. I mean, if you think about science, right? Just sometimes you just see something, you have a vision, and then you can start. I often not able. Sometimes I understand something and I cannot tell you what I'm understanding. I just know that I understand it, and then I spend the next month trying to find the word to say it.
And there are so many examples of scientists saying what you're exactly saying right now, right? That almost every scientist probably has had some experience of that feeling of just seeing something intuitively, not knowing the exact explanation for what uh, they're intuiting, and then working on it to come up with a way to make make it more understandable. Yeah. Um, I mean, if you just look at the architecture of transformers and the way LLMs are architected, I don't see a place for that just yet. It seems like they are extraordinarily capable of learning about vast amounts of information in that's inherent in human written language. Like if I just think of what an LLM is doing, given a prompt, it's capable of navigating some extremely large conditional probability, distribution to find the next token. Uh, and that conditional probability distribution is far, far larger than anything any single human works with. So I have a feeling they have because we have built them to be so big and there's so much computing thrown at the problem, they're probably much more literal about their world models,
Mm.
right? And we're not forcing them to not do that in the way they are trained. If you take that simple example of this two-layer transformer that they've discovered grokking in, right?
Mm.
Now, that to me is an example of a small neural network that was being trained to do modular arithmetic. And they just happened to discover the fact that if you train it for long enough, and if you have a certain amount of regularization that is there in the objective function, you're forcing it to come up with a simpler solution. And then it finds one. It finds a much simpler way of solving the problem, which is more abstract. Uh, and it doesn't seem like LLMs are operating at that boundary right now. I don't. They're too big to overtrain anyway. So we don't know whether they've been pushed to the
Mm.
point of grokking.
Okay,
But
that's
you
an
can
interesting
but you can
conjecture. Maybe you could overtrain them in a way that they would compress more.
if you and that we know that from these small neural networks, right? We can only do it for very, very tiny ones, like literally two layer,
Mm.
two transformer layers, and teaching them simple tasks like modular arithmetic. And we see the grokking. We see them using far fewer resources at the very end of that whole process when they have grokked, and they literally embody, the networks embody the structure of the solution. Whereas a bit earlier in the training phase, they are using a lot of their weights and they're doing, they're literally memorizing the data. And at some point they say, okay, we don't need to memorize because the network figures out the more abstract solution. So it doesn't seem like that's what LLMs are doing at this point. I think they are much more at the phase of learning about everything, uh, that is there in the data. And it's a pretty amazing achievement that they're able to get something out of that whole thing. But what
So
if you
I
push?
feel is your idea
So,
that our evolution really grokked our brain so that
I mean, I hadn't thought of it that way, but evolution would have pushed the system towards energy efficiency. Has to, right? I mean, it has to be a thermodynamically efficient system, otherwise evolution weeds it out.
and
So
information compression, there is not that much genetic bandwidth.
yeah. So sorry, say that again, Luca. I'm not sure.
Compression as well. You really need to compress the information. The
Yeah,
bandwidth in our DNA is not large enough to store too much.
right, right. So all of those things is probably pushing the system towards figuring out more abstract, more efficient solutions to a space of problems, to a set of problems, right? So when we learn something symbolic, suddenly we are capable of applying that symbolic knowledge to a vast array of problems, not just the one pattern that we were trained on. And LLMs right now, even though they are able to solve this vast array of problems, they're probably doing all of that through individual learned patterns rather than some abstract knowledge of that pattern.
Although, this is one of the things that I tend to disagree with symbolic people because I feel they look for intelligence in the wrong places.
Hmm.
They think that intelligence is this kind of mechanical operations, A to B, and I think it's kind of I mean, and they say, oh yeah, like a neural network cannot solve 10,000 steps of Hanoi Tower, and just first of all, humans can't as well. So,
Yeah.
and any stupid programmed algorithm can. So, how is a calculator intelligent and a human is not? And now you're saying that LLMs are not intelligent because they resemble more the human than the calculator. I've heard the calculator so many times, but I mean, again, I have a strong opinion. I think they're a bit bitter.
Yeah, no, so when I talk about symbolic sort of representations, I'm not necessarily talking about uh, so when you look at the grokking network, you have to decipher the weights, you have to kind of go and look at the weights to figure out that there is a representation of in the weights you can extract a symbolic representation from the weights, right? But the network itself doesn't necessarily tell you what that is, right? It just becomes that.
Yeah.
So I wouldn't be surprised if there's a lot of stuff that we do, our symbolic symbol manipulation, etc., is just the outcome of neural networks in our brains. I guess you can call it grokking. I'm not quite sure. I mean, we understand so little about what's happening in our brains, so I don't want to unnecessarily speculate here. Uh, but a system, our systems, biological systems have been pushed by evolution to thermodynamic efficiency, information compression, and all of those things. And that must be forcing levels of abstraction that are currently not being seen in LLMs. Because we haven't enforced those limits on LLMs. We're just throwing as much compute as necessary, as much parameters as necessary to make them learn more and more and more. Maybe there
Yeah,
is
and we
another
are
way.
stopping when they look intelligent. So maybe that's, I mean, as you said, I mean, it is it's a very good argument. It's that first of all, we probably will not be able to train them long enough, but
Yeah,
maybe if we did, then we actually will. But also, we stop when we are happy, and
yeah,
these are the fact that LLMs are very superficial intelligence. So we are happy. When we are happy, we are happy. There is no reason to keep training more, which and then their superficial intelligence will not even increase. Maybe it will even decrease, because
yeah.
maybe they will start to forget a bit more. I mean, there is this old information bottleneck principle. Probably you followed like the news stories. It was a few years ago. Then it's been debunked. There's been, but I
Mm.
don't know. I think it's an interesting idea, and actually, some people are taking it more seriously nowadays. I think it's but we are not, well, at least like this company, they're not really looking to have, they're getting what we want to get, which is
Mm.
helpful assistance. And if you think about,
Yeah,
uh, actually creativity doesn't help that much.
yeah,
Often you don't want it because it's unpredictability. I mean,
yeah.
honestly, I mean, I'm all for science, I'm very curious, but I don't want to get there. I don't think it's good to get there.
Get
Like,
where?
you know,
Get at
get
human-like
at the
intelligence?
point in which we cannot really distinguish between humans and machine. I mean that for me it's a bit of I'm not sure what we have to gain from it because we have humans, so we're not getting anything new at the end of the day. I know that some people are looking to sort of machine code, but I think those people should maybe start their own church or something. I don't think that is
Yeah, yeah,
science. And I don't think that you can train on humans and bootstrap something that is more than human. I feel that we are exactly getting out what we're putting in. Um, there are so many. If we actually reach the stage in which we have kind of more human-like AI, and again, it's a complex issue because what does it mean human-like? Because current LLMs are more, strictly speaking, intelligent than most humans. That's just true. They are also not capable of doing what plenty of less intelligent human can do.
yeah,
We just figure out that intelligence is not what really the key factor of what makes us special. And I think that was a big discovery for a lot of people, that
Mm.
you can answer competently a PhD-like question and then, but you still don't have anything that you lack the kind of thing that really make
Yeah,
you a human being that are lower
yeah,
than our intelligence that will not even understand the question, will still have.
yeah.
That's very interesting. But how do you see that? Do you think that is good? I don't think research should stop because I think it's impossible to stop research. People will always be curious, right? I just personally hope that we will fine tune and improve on what we have, but we will not reach the point in which we will actually need to consider these questions because I think it will destabilize society so much and it will also create so many ethical problems that I'm not looking forward to. I'm looking forward to a world with very good AI systems and not looking forward to a world with AI people. I don't know how you see that personally.
Um, I think for me, there's a difference between what I would like, which I agree with you, that there is something special about what we are and the way, like for instance, someone had asked me, you know, a lot of writers get asked this, do you use LLMs for your writing? And my response was, I would not use LLMs to help me write, because writing for me is what I do that gives my life meaning. And I'm not going to sort of give away that uh, process, hand over that process to a machine, because then whatever it is I am doing to give meaning to my existence has now vanished, and I don't want to do that. But saying that, I might use machines for something else. Like, for instance, I definitely use LLMs for trying to learn about, matrix manipulations or
Mm.
linear algebra. That's totally fine. And so different people will have, and a mathematician might say, okay, I'm not going to use an LLM for doing mathematics because doing mathematics is what gives me meaning. So the mathematician may have a different set of things that they might not want to use a machine for. So I think there is something about what we are as humans and what we do, and what we choose to do in our lives, that gives us meaning, and we would hope that those things are not given away to machines, right? So in that
Mm.
sense, I agree with you. I think we should hold on to whatever it is, and different people will have different things that make sense to them. I have no problems
Yeah,
using I have no problems using a diffusion model to generate images, because I am a terrible artist. I can't draw for anything. So, uh, but I would not let it write for me, because writing is what I find meaning in. And so I think we'll continue doing that. That's more from the perspective of what I would like, and there I'm in agreement with you. But I have a feeling we may not be able to stop this process. And that might have more to do with the nature of the human self itself, right? So there will always be humans who will be both extremely smart and who will also be very, very motivated to build these
mm.
machines for reasons that could be economic, that could be completely egocentric,
Or just no, but I mean, myself included, I'm not. I don't think that we should stop researching, and
yeah.
I do think that if we quench our thirst for knowledge and for improvement, then we lose part of us. So that's
Yeah.
now my argument is I'm not convinced. I know that a lot of people think, but I think the specific scaling that we have seen was a reflection of increasing amount of data
Hmm.
by large amount. I don't see this leading to the future in a particular way because we kind of almost you can definitely increase, but it would be very dispersed data. So you will have I don't think you can. So now you can see that an LLM is very good at doing standard topics, right? If you ask a calculus question, will 98% of the time answer it perfectly. Okay. But if you ask a question in between fields where people did not study, it cannot. Why? Because there is no data there. So it can do a decent, it can think along. It's
Hmm.
fine. It's okay. Not great.
Hmm. Hmm.
We don't have data where there isn't data, that it
Yeah.
just remains of the fact. We need to discover
Yeah.
ourselves. So AI as it's understood now is bottlenecked by us. We need to first create the data, just discover those things, and then you can fit them and you can get smarter. But people think that AI start to create data itself, and that's something we have never seen. So you can have that, but it's a bit of faith. It's not something you can extrapolate from what we've seen. We have been there was this huge barrier of potential that was the data that we already accumulated as humanity so far, and we
Yeah.
can do a better job, but not by order of magnitudes.
I
And
agree.
once you're
Yeah.
accosted that, well, it catched up, but then it's not obvious. We need an alien civilization to put new data for getting, you know?
So that's and that is the point at which we have to wonder whether what we have today is really the correct kind of AI, right? I mean, uh, so like somebody was pointing out, I don't know where I heard this, but somebody was talking about, let's say the LLMs had been trained with data about physics that ended in 1915, and it only had knowledge about all the physics that had happened until 1915. Would it be able to come up with Einstein's general relativity? And the answer is no, right? Right now, we don't have AI models that can do that. But it's also true that humans did it, right? Einstein did it.
One.
So, yeah, well, but if it hadn't been him, somebody else would have,
That is true.
right? So the thing there is that, and if we accept the fact, and this is where there would be debate about what we are as humans, but if we accept that we are also information theoretic computational machines, very, very sophisticated, but nonetheless, uh, using those systems, then what if your curiosity as a scientist eventually led to the building of a machine that had that capacity? You would not stop. As a scientist, you would want
No,
to do that,
no, we
right?
shouldn't stop. I don't believe. I don't believe.
Yeah. So but
First
if
of
you
all, it's
don't stop,
unstoppable. Yeah.
yeah. So if you don't stop because of the curiosity that you have as a scientist, then I don't see how we're going to not figure out what our brain does.
Yeah, but remember, like maybe this grokking really, I mean, we are talking about millions and millions of years of evolution, you know. We are smart, but are we that smart? Uh, we had this huge increase, and then we feel okay, now it's going to be exponential so far. But like physics has an exponential increase of knowledge from the 20s to the 50s, but we
Mm,
stop growing exponentially.
mm.
I would like to see, maybe we will get there at some point, but whether we'll get there soon, it's not obvious to me. And if I ask, yeah, it's been what has happened has been mind blowing. I think though
Okay,
we are
okay. Here's a
exhausted.
here's a thought experiment. If you ask these questions to somebody in the 1920s, they would have probably never thought of machines that we have today. Impossible, right?
Mhm.
So our ground for arguing about what is possible now is starting with what we are seeing with machines today, and we want to put the stop just a little bit ahead, but we want them to go a little bit ahead, but not too much more. If you had asked the question for somebody in 1920, they would have put the barrier at 1940 or 1950 and not too much more. So I think it
Mhm.
also depends on, as a human, what era you were born into, and right, and your makeup, your cognitive makeup depends on the fact that you are the age that you are, and you are working with the technologies that are around you.
Mhm.
40 years from now, people will have a very different sense of where the next step should be,
Yeah,
where we
that's true,
should
but it
stop.
could be in completely different things, right? For example, like if you look at what people were predicting from the 50s,
Mm,
we very much over deliver on some things and very much under deliver on others. Like people in the 50s were imagining colonizing this. If you read the science
yeah,
fiction from the
yeah,
50s and 60s, we are currently in this year, we will be colonizing the solar systems at a complete minimum. And people were genuinely expecting it,
yeah,
that in
yeah,
those 50 years, we will have been obviously colonized. No, we didn't do any progress at all in that direction at all, because
mm,
it's very hard. It just turns out to be very hard.
yeah,
Like people sometimes say, "Oh, why don't we have flying cars?" Because there isn't the physics for flying cars. We cannot make up physics, you know. We can
yeah.
work with what we have, and it could be that there would be we discover something enormous about AI, but maybe something all enormous else needs to be discovered. And maybe the reality is that that's a process that takes millions of years of evolutions, and you cannot brute force it. We don't know, right? So maybe we continue,
This
maybe we
is
won't.
this is sort of the argument that Wolfram has, right? If I remember right, I'm not sure. I might be completely wrong here, but my understanding is one of his arguments is that it evolution literally needs to take place the way it did for, you can't speed it up. If you want this result, you need to go through all those computational steps. Uh, and yeah, but it's possible. I mean, there's no way for me to. I'm not steeped in the science or the math of it to have any insight into how this is all going to play out. I'm just thinking, speculating aloud that if there is no in principle reason for differentiating between us and machines, then we might get there at some point, and
Mhm.
and yeah, then all bets are off as to what happens.
Yeah, I mean, I think that this is a great time to be alive. I mean, I'm not a negative person, and so some people are negative about everything. I think this is, I mean, first of all, I'm scientist in this field, and I'm fine in the middle of scientific revolution, right? It feels like being a physicist in the 20s, so that's
Yeah,
amazing.
yeah,
And I think that these are very useful. So I think I have a bit of different bind. I started a bit to say, okay, I don't want to use it for writing for math, but what I figured out, and I think it's a balance. I didn't learn it entirely, right? But I just feel so far, I mean, those models are not good to write a paper or writing a book. If you ask, it would be garbage, you know? They're very good at writing a paragraph or at rephrasing it, you know?
mm, mm,
Um, and I mean, that's a matter of taste. I'm personally a decently lazy person. I really focus on the main ideas, and I just often don't have the patience of really crafting everything. So what they quite often do is that, for example, I give instruction for individual paragraphs, or I just usually start the draft and I say, oh, can you rephrase it in a bit of, or for the math, I ask it to do the kind of things I don't have the patience for doing, like, or the time, which, okay, can you fill up the details? I mean, I know more or less what the structure of the reasoning is, just write it out in full, and I'm still writing or doing math, because the machine is actually not putting much creativity at all. It's kind of doing the boring part for me. So that really feels that actually is unlocking things that I couldn't have done before, because I wouldn't have the time or the expertise. Sometimes I have an intuition, but I don't have immediate expertise to do it. And often GPT will recognize, oh yeah, this is the standard. Okay, then it's standard, perfect. That's exactly what I needed. I can work as if I have a team of mathematicians around me, not the best in the world. Just that for me, it's. I also see the risk that then if I get used to not doing stuff, then I lose the skill, and then I think it's this very careful balance to see. I think there are a lot of things I can do now that I couldn't do before, so that's very cool. But then if I get addicted, then maybe I just lose what make me creative and make me productive. And this is something I think it doesn't have a simple answer. I do think that we need to find our own balance on this kind of things. And I think it makes a bit of a difference for you and for me, I guess, because I feel at my age, with all the things that we wanting to do as a kind of professor, between writing grants, writing papers, one field that needs to be of this enormous amount of productivity, and then I feel, well, but if I want to write a book and I say, okay, I can take my time, just then probably I wouldn't use it, because I feel okay, but then.
That's what I mean. That I think for you, the meaning making for your life comes from doing the science, right? It's not about the writing the grant proposal or should. So you would have no problem using it for that. For me, my craft is finding meaning in the writing of something, figuring out what the story is, figuring out how to write it, and even the words that I choose, the sentence structure, etc. All those things give me joy, and I would not want to give that away to a LLM. But if I had to understand something in some other field, I'm completely open to using it. It makes total sense. Right? So I think we'll all choose different things for which we will use the AIs, and hopefully for other things we won't. Exactly for the reason that you said. I don't want to lose an expertise that has been built up over 20 plus years. It could go away very quickly if you depend on a machine.
Yeah, but the flip side is you can really gain expertise in something you wouldn't otherwise, because as you said, it's just sometimes you just don't have to, you don't have the book at your disposal, like, and here if you have an idea, you can query it, and sometimes there is something you could learn that you didn't even know it was there, and you wouldn't have read the math book or whatever.
Yeah. I mean, I honestly, the last week of trying to figure out the physics stuff that has inspired generative AI. The irony has been that I've been using generative AI to learn about how physics has inspired generative AI. That's pretty amazing, right?
Yeah, I mean, for the physics, I think we are starting to experience a bit of a renaissance. I mean, I have a bit of a stake in the field because I think I'm contributing a bit to this. But I do think that finally we are seeing actually physicists trying to jump back in actual core AI. Because for a while, since the deep learning revolution, a lot of physicists, I mean, obviously, right, you have the Boltzmann machine and stuff like that. But then after with straight neural network, most physicists kind of went to really application to physics, right? A lot of people have been doing like application to field theories, but rarely actually trying to or understand what machine learning does, like it used to be like in 90s and 80s, in which there was really a lot of physics. And I think that's coming back. I think diffusion is a big reason. Just diffusion takes a lot of physics and diffusion. I mean, it just comes from physics, but there is also a lot of physics to be done.
Right. And I would also imagine that people who study complex systems and dynamical systems and just treating these things as complex systems with very specific properties that you can study from all the physics of complex systems that people know about, right? There must be ways in which machine learning, deep learning systems can be studied.
Yeah, I mean, recently, Mark Mazard, for example, was one of the pioneers of the kind of thermodynamics of disorder, just really started to focus on diffusion models. I feel like it's a strange situation in which you see a lot kind of senior people entering the field, and not really coming that much from the bottom up. It's a bit of an inverted situation in which there are quite some senior people actually making. I think there is, when I talk to physicists, often there is a bit of a problem in academic culture in physics, in which they have a kind of strong competition for a few positions, and they tend to be quite conservative on their choice of topic, because eventually they are evaluated by their peers. And if they live in a bubble in which everyone is just doing, let's say, standard spin glasses and stuff like that, it's a bit dangerous for you to actually, okay, and I want to try to understand kind of machine learning, you know? It's strangely enough, a lot of academic physics is a bit timid from the young people, you know? Which could be very productive if they actually move like to diffusion. There is a big need now, like with the young, we're starting to do like information theory of diffusion. It's just really beautiful, and there is a lot of stuff to be done. And there are just few people in the world who are doing it, you know.
So who is working on the information theoretic diffusion?
So we are one of the labs doing it. I've recently we had in the lab we had Akil. What is his last name? He had a very nice kind of neural entropy paper.
Anil,
yeah. So it's a quite young like professor. I think now at Yale. It's a that is really pushing. Huh?
I think it's postdoc.
Okay. That is pushing like this really connection with physics and information theory, information thermodynamics. Very beautiful stuff. There are, actually Kong is going to come in our lab today. They are actually developing, there are some authors that are really developing quite a beautiful information theoretical framework. I'm starting to work with Giulio Francese in France, Eurocom, in which again their connection with it's a decently restricted group of people. There is enormous amount of things to be done. It's very practical. So the strange thing is that these things just work very well in straight machine learning application. Like now we're using information theory to train diffusion model, and we can easily beat highly engineered baselines just using theoretical principle from information theory. Actually, the Yan paper is a good example in which, for sampling diffusion model, we could beat highly engineered EDM baselines. So that's a field that is very exciting for me because it's both elegant and theoretical, and the elegance is very high there. You have an extremely beautiful formula. It's also very practical. Usually this formula will buy you, and there are so few people that actually do it that actually there is it's if you are someone who kind of wants to make a difference both in practice and in theory, I would really recommend information theory. I think that's for diffusion at least, and I think for LLM will also pay off. I think that's going to pay off biggest theory in the future. I mean I'm also doing it, so
that's very nice to hear, because yesterday at this talk when I was asked about where do you think physics will inspire new models in machine learning, I didn't really have an answer, but this is great. So diffusion models themselves are being now improved and understood by using principles from information theory and physics itself.
So the example like that I can give you is that diffusion model have this concept of time. But time in diffusion is arbitrary because essentially it's your model specification. So you can change your definition of time and nothing will change. But in practice, you're working with a finite computer, and actually if you rewarp time, you will get very bad performance. Okay. So we really took this idea of physics to the work we did with the young like last year, said, okay, but in physics, time is fundamentally entropy. That's the way you kind of keep track of time. And then we found, initially we didn't know, but we found that actually this estimating entropy in diffusion model as this completely beautiful formulas that are not just beautiful, but super easy to estimate in practice. We found out that the entropy rate is just a training loss, essentially. There is some scaling, but essentially is what people was already doing. And then straight off the box, without any parameter, we could beat very highly engineered baselines. And now actually we're going to be able to show it soon, but now we are working with using it for training. And again, it's going to be quite impressive results, but essentially without parameters. And for me, it's quite shocking because I love the theory, but I've also got a bit skeptical to say, okay, does it buy you something? And before starting to work with information theory, I would say I do some physics and theory of diffusion because it's beautiful, but I'm not expecting to get, I was expecting to get something, but not mainstream level of performance, but actually, that's a very good stuff. And that's, I think the theory now is limited by the very few people who work on it. And most people who have the expertise don't really understand machine learning enough. I think once you get someone and understand what the problems are, understand what machine learning is all about, what problems you want to solve, and understand the techniques and theories of information theory and physics, I think that person can make a huge difference. Essentially, there is this field of stochastic thermodynamics that essentially they're studying generative diffusion, and they've been studying generative diffusion since the 90s or 2000s, and there are some areas of non-equilibrium thermodynamics that are identical setup to generative diffusion. So you can actually take their. It's just that they solve different goals. So the problem is that if you those people who do it, there are a lot of experts in this field, but those people who do it, they wouldn't know necessarily what is important to solve in machine learning. So they have the skills, but they don't know what to do with it. But essentially, for a lot of problems you want to solve, probably they're already somewhere in a physics book. I think this is similar to what's happening in finance, in which with the Black-Scholes model, people realized that they could just plug in from physics books, like solution relevance from finance. And I think we are gradually having this realization now. We come from a field that has become very allergic. People are very skeptical that theory would buy anything at all, So I feel we need to be a bit against the mainstream idea that you don't need theory at all, you just need engineering. Which it works so far. I'm not saying it's a bad philosophy. I think it's for most things you have to do, it's a good philosophy. But if you are someone who likes theory, you don't have that much competition, and there could be some very, very mainstream good results that you can get from it. From doing what you love.
And, honestly, if you look at the field of machine learning, it's only in the last 10, 15 years that we have sort of started focusing more on the engineering, right? Pre-deep learning, which is not that far back, it was still kind of principled in terms of how algorithms were developed, and there was always a mathematical rationale for doing something, right? The empirical stuff is only post-AlexNet, which is 2011, 2012. So we're only 13 years into this field. And so it's not surprising that people are throwing all this money and effort just to scale things up and do it empirically without worrying about underlying mathematical principles or physical principles. But the fact that it will change again that's great to hear. And because
I don't know, but
because for most of the history of machine learning, it has had a mathematical sort of underpinning that has fueled it, right? And in fact, the people who don't like deep learning are bothered exactly by that there's not a strong mathematical foundation or rationale for developing the systems that we are developing. And so with the example that you I was going to say that the example that you're giving now is kind of the counterexample that, okay, hang on, we have these principles and we should be able to use it.
Then I think of because that it comes from the fact that the mathematics of neural networks is almost impossible to solve. It's completely intractable. The beautiful thing of diffusion, and I think you can get it from autoregression as well in some cases, is that you can say an enormous amount of things about the methods without ever referencing the network at all.
Okay, got it.
So that's the thing that works. You just have to say, okay, you can kind of work around the network. At some point I want to write something, say the art of talking about neural networks without talking about neural networks, because essentially it's what we're really trying to do. And not just us, also a lot of people from physics. Essentially, you can study the problem from a kind of learning theory perspective and say, okay, there will be a network there, it's a learner. I don't care about its details. I know that it needs to solve the problem so that I can understand mathematically, And from that, you can get a lot of insights. Like the whole entropy calculation, you will use the network as an approximator, so you can use the network, but the theory doesn't reference it. The theory could work with any sort of learner,
Right.
And that works. If you try straight to kind of include the network in your theory, it's just known that we have no idea how to do it. People are still trying to do that with two-layer networks and at glacial paces.
Yeah.
Yeah.
No, it's amazing.
But this is still like AI is taking from other fields like physics and math. But like, do you think AI will, or like studying neural networks will give rise to some new math or physics?
That depends on how well you understand the neural network, right? I think the very simple example of that, of how that thing was a two-way street, was Hopfield networks, right? When Hopfield networks came about, they were inspired by the Ising model. But then the big impact Hopfield networks had was not on machine learning, because they're really not used, but they had a big impact on people studying materials. And so I think it are but then Hopfield networks are very well understood mathematically. So and so it was possible to go the other way. And what Luca is saying, that we just don't have that level of understanding of deep neural networks. So I don't have an answer for that. I wouldn't be surprised.
I think that there is one good example of this already happening. Again, coming from generative diffusion. By looking at generative diffusion, like physicists, for example, the group of Montanari currently is in where is Montanari sitting now? Anyway, it's one of the major physicists in the theory of disordered the system, and they are developing this idea of stochastic localization for sampling essentially physical system, like Ising models or related physical systems being losses. The theory is essentially completely straight taken from generative diffusion theory, and it seems to actually solve a lot of very interesting sampling problem in statistical physics, which tend to be quite the core of what often statistical physics does. So for generative diffusion, at least I have one case in which the math of generative diffusion is actually doing something new in physics for purely physical things, even without network, just for deriving sampling distributions. Generative diffusion is similar to Hopfield network. It's something mathematically contained, mathematically very rich, that can be analyzed in a very straightforward way. Yeah, exactly. I do think that there is so much things that physicists could do if they start working on generative diffusion, because there is a bit of level of kind of intimidation that, again, you only see kind of actually big players doing it, just very senior physicists. And you don't see that many young people jumping into the field. But I do think that once you are a bit brave to jump into the field, you can even contribute to physics. So, like, for example, now Giulio Birioli, again, very well-known physicist, now really focusing almost 100% on diffusion, is really trying to apply this for like renormalization groups and recontextualizing our understanding of the renormalization group in terms of generative diffusion, and there is something genuinely new. It's that diffusion processes are very well known in physics, but the way generative diffusion is done and the level of details that we're actually studying it is giving something new to physics, that they knew the process, they knew all the math, but they never took it seriously at the point of figuring out how rich it is, because it's surprisingly, it's a kind of process that the first time you hear about, it sounds trivial, because if you start something here, you will get something like a mixture of Gaussian. You just, that's a kind of a toy model, and actually there is a kind of an enormous amount of complexity and math and beauty just in that, which of course people working on non-equilibrium thermodynamics have been studying. But non-equilibrium thermodynamics is an insular field as well. It's a field that most physicists don't even study, so it's their own community. There is just a lot of complexity in out-of-equilibrium system that you need to evolve with simple rules. Just a lot of complexity that you wouldn't expected it in a very elegant way, not in a...
No, it's amazing. I mean, you would obviously know the story of diffusion models itself, right? How it came about when Jascha Sol-Dickstein was at Stanford. He was working on generative models 2013 or so, but he would go every week to Berkeley to be part of a physics group that was studying non-equilibrium thermodynamics. Two separate things. Like on one hand, he was working on on one hand, he was trying to come up with generative models to explain how the brain works, and then on the other hand, he was just doing his physics meetings with people at Berkeley. And then the light bulb went off when he connected the two, and we got diffusion models.
That's really cool. I mean, for me, that was really a game changer. That, first of all, now theory exists in state-of-the-art machine learning, and that's something we have been starving for a long time. You know,
Yeah.
we
Yeah.
just didn't have like substantially interesting theory to do. And now it's there. Now it's on the table. Now, if you are someone who care about elegance, about beauty, but also care about doing stuff that mainstream AI people care about, well, just work in diffusion. You know, that's and it's an endless well. When you think you have understood it, that there is something else entirely that completely surprises you. You know.
So, do you feel like all this effort that's also being done to have diffusion-based language models, is that a valid approach?
I'm excited. I'm not excited at the way they are trying to do it.
Mm.
Yeah, no, I do think a lot of people see that as, I mean, first of all, it just pragmatically LLM did not change since they've been invented.
Mm.
You know, so it's kind of difficult to actually think how to improve them.
Mm.
Diffusion, language diffusion is an open game. It's something that if you're an ambitious scientist, that you want to have your chance of having your mark of diffusion, just work on language diffusion, because the game is not, there is not been a winner yet, you know. There are several competitor options. They're mathematically different. It's a bit of a zoo. It's not like diffusion for images. So there you can really be the one just unlocking language diffusion. I think it's very promising. I think it's super exciting as a researcher. As I said, it's an open field that there are things we understand, things we don't. Requires understanding of engineering, but also understanding of physics, understanding of information theory, and I think it will pay off. That's my opinion.
Wow.
And if you think about cognition, it becomes a bit less literal, you know. A diffusion model can look kind of, can have a vague understanding of the far future and a more concrete understanding. So it thinks, if you think about how diffusion model will think, and you need to integrate an autoregressive aspect, right? Because standard diffusion model generate everything at once. So you cannot generate the user at once. So then it needs to move forward in time somehow, you know? So the way I see it is a kind of moving window that look at the future, and it looks to the far future with some level of kind of coarseness, and closer to its time, it works kind of like an LLM, you know? So the vision I have is that it's a kind of, it will be an hybrid. What we will get, it will be an hybrid. Now, regardless to the kind of philosophical aspect or cognitive aspect, there are very good mathematical reasons that if you unlock language diffusion, it will replace LLM. Okay, and the reason is that you don't need to do better than them. Language diffusion, you don't need to do have better performance. Essentially, it's much easier to accelerate a diffusion model that is work. Autoregressive model works token by token, and trying to skip tokens is hard. You can do that. You introduce errors. It's a mess.
Yeah.
Okay, it's possible, but it's hard. A diffusion model, and by this I mean a continuous diffusion model, which unfortunately is not the mainstream approach now for language diffusion, for reasons that are debated. But a diffusion model is much easier to accelerate, essentially just math. There is a vector field, you just open your numerics book and you accelerate it, you know?
Wow.
It's I mean, you understand the math. The point is that the difference is between continuous, like think gradient descent, right? You have a gradient. And think about the discrete optimization in which you have finite difference, but the function is not differentiable. Okay? It's a huge difference. In one, you need to search coordinate by coordinate, like sampling token by token. In the other, you just cut through to the gradient.
Yeah.
Continuous diffusion is differentiable, so it gives you a way of updating everything at the same time, which make it very easy to accelerate. So once you have a model that reaches the same performance of an autoregressive model, most likely can do that with much less money.
Is this somewhat analogous to the work that is happening in transformer-based LLMs, but where the auto-regression is not being done for every token? You let the LLM or the transformer kind of do a lot of its navigation in the embedding space for a few cycles, where it's moving around in continuous space before you generate the next token.
I don't think you could do that in continuous, but it will still be autoregressive.
Eventually,
I'm not super familiar with that literature, but the point is not whether it's continuous or discrete. Well, no, I mean, if it's fully continuous, you could probably do it. I don't think they're currently doing it, though.
At some level, you have to enter back into discrete token space. So, I agree that it's...
It can be. If you look at continuous autoregression, it could be that you actually try to speed it up by looking the gradient direction. I do think that that's true. I don't think that there are papers that actually do it, but I don't know the literature enough. But the fact of diffusion, you can do that also with discrete tokens. If you do continuous diffusion, which means that essentially you are kind of embedding the tokens in space, and then you diffuse continuously. And that, unfortunately, or people are convinced nowadays that it doesn't work. Maybe that's true. It's just that usually it's someone else said so, or often you talk to people and say, oh, but if it worked, people will have made it work by this point. But I also understand that the literature moved very quickly, and I think there are a lot of rumors and and I also know that nowadays, even in top labs, when they drop a diffusion model to something that is not images, often is severely under-optimized. So the fact that they didn't do that in the very brief amount of months in which people decided that it didn't work, I think we moved so fast that there are some things we decided that don't work. Like before, like I think at beginning neural network, people say neural networks don't work. Okay, we don't do it, right? And that will just work. So my opinion that would just work, but I don't know. But objectively, what people are doing currently that they call language diffusion, unfortunately, is essentially autoregression. Because what they talk about language diffusion is so-called masked diffusion, in which the noise is not Gaussian noise or is not flipping, it's just replacing tokens with a mask token. It covers it entirely. That's essentially out-of-order autoregression. You are actually doing autoregression without a fixed sequential order, but it doesn't change too much the math. In fact, you can say that if you want, you can say that an autoregressive model is a diffusion model if you want. If that would be, you just need to fix the order. The point is that it's not a diffusion model in the sense it's much closer to an autoregressive model. Now, I understand why companies like it. It's because it's the simplest step you can do. And companies are very conservative nowadays. So they rarely will spend a lot of money on something unproven. So for them, mask diffusion is kind of, it's so similar to regression that the whole barrier of optimization is already there. You don't need to change that much, you know? So that's why I'm super excited about language diffusion. I'm not super excited about what people mean when they say language diffusion nowadays for 90% of the time, because for me, that's slightly variation on autoregression. That's if you lose most of the magic of diffusion. I mean, maybe I'm wrong, right? I'm an opinionated guy, but that's I think that my hope are in more intrinsic form of diffusion, like continuous or uniform noise, or just things that are more entropy increasing processes. First of all, mass diffusion is an entropy decrease process. As you mask something, you lose entropy. Diffusion is an entropy increasing. As you add noise, you increase entropy, you know? And for me, the essence of diffusion comes from the entropy increasing part of the forward process. If you decrease the entropy, you're doing something else with a similar mathematical infrastructure, you know?
So from a machine learning perspective, if you have that entropy increasing part in your equation, then that is going to help with generalization, right?
Possibly. I mean, autoregression generalizes well as well. So that's possibly, yes. But both methods generalize because it's essentially the fact. So if the forward process is entropy decreasing, the reverse process need to re-inject the uncertainty, right?
Right.
So the entropy comes from the reverse process alone. So essentially, in a generative diffusion model, the entropy comes from both, you know? Kind of the generative entropy uses the entropy of the forward process. Actually, the theory is quite beautiful. In some sense, if you look at generation and generative diffusion model, there is almost, you will have that the entropy decreases as you generate, just that's come from. But there is a kind of paradoxical increase of entropy. Okay, this is what we call the conditional entropy rate. And it will never be enough to actually make the term is counteracted. So you will never see that the entropy decreases, that the entropy increases during generation, but there will be time in which the entropy stops decreasing. You know, during the generative process. That's creativity. That's the model is using the entropy of the forward process to generate. You know, so the randomness has been channeled to create generation. It's really beautiful. If you actually look at the kind of the non-equilibrium physics, and you can really see that from the entropy rate, you get. It's actually not that complicated. Actually, it's just if you want.
You've given me ideas on what to sort of look at next, and you know,
I will not. I don't know if it's too French. Obviously, that's.
You know,
for
it
me,
sounds
like
beautiful.
Yeah, it is beautiful. Like I don't know if for the general audience would be maybe difficult to propose it or something like a book, but there are the more I study diffusion, the more there are things that I just find just mind-blowingly beautiful, and it's honestly, there are some aspects of generative diffusion that generally gave me kind of religious inspiration. There is this kind of principle that I discovered that essentially. So imagine that you're playing a game of 20 questions. You know the game of 20 questions.
Yeah.
So usually, as you play, let's say I decide a word, and you will ask questions to me. Okay, and at the end, you will kind of reduce the entropy of your space until you have a single point. Okay, so you can look at kind of the information gain in terms of information theory. That correspond from that point of view. Imagine that there is a single final answer, right? Now, the insight that is quite connected to diffusion is that the game works identically if I were lazy and I didn't come up with the word. You will still ask these questions, and imagine that I answer a complete randomness. Okay, so you ask me, is it a mammal? And I flip a coin. I say yes. By the nature of the process, it needs to stop. Because the entropy will go to zero. So from your point of view, you will not be able to distinguish that I didn't make it up. So this is the same what's happening in generative diffusion. In generative diffusion, in the forward process, you start with something like an image, and you add noise until that image is completely removed. Okay. If you invert the process, so the image existed all along. It was always under the noise. It just at some point is invisible. If you do the generation and you invert the process, there is no image. The noise will gradually shape itself into an image. So where is the image coming from? It comes from these random answers. It's
at
like
every step.
At every step, there will be a bit of noise added that is channeled by the network, kind of blocks. Essentially, the noise acts as an oracle that essentially can only say the truth, because everything that the noise says is law. Like in the game of 20 questions, when I forgot the answer, I flip the coin, but after it's fixed for you. It's a mammal. You need to live with that. You know? So everything the noise says is law, but the network can stop it. The network can block the noise from having an effect. And that's the only thing the network does. In generative diffusion, the network is a filter. The network cannot decide. That's a very philosophic, important point. The network is deterministic. A deterministic system cannot create anything. What the network does is stop the noise on specific direction, so that the decisions are only made when they're admissible. At the end of the day, the noise will have made all the decisions, and you will get the final image. You see? So now we have an equivalence between two words, one in which the image was created at the beginning, and one in which it was kind of synthesized by complete randomness. And those are mathematically equivalent and indistinguishable. So the religious insight I had is that it means that essentially you cannot distinguish a word. If you think about the materialistic idea of the word, in which there is only randomness, and a religious idea of the word, in which the word is created and all the decisions reflect that creation, those two things are not distinguishable from inside the word.
Wow.
I think it's profound. I think it's
very profound. Yeah, no, it is. I'm now inspired to learn more about the math of all this, and absolutely. I'll look up your work now and try and understand it. I'll come back to you with questions. We're trying to
figure out on the spot. I mean, I don't have the answer. I just feel that there is a lot of things, both on the math and on a conceptual level. It's just that, I'm a bit excited about this thing. So.
No, it's cool. It's very nice. Yeah, this is the kind of from my perspective, as as someone who is learning about this and then using what I've learned to communicate these ideas. This is the kind of stuff that excites me, right? Because eventually, it's these principled things that somehow shed light on something deeper. That is the interesting part. Right? Yeah, algorithms are fine and all that is fine, but if suddenly you see this something, a kernel of seeming beauty or truth at the end of it, that makes for a beautiful learning experience.
This is generally something new that people have not been thinking about. So also, like we are trying, for example, now to write an opinion paper on a possible role in the brain, and I think there are a lot of things that just it's a very natural and biological way of understanding how things are done. That is not true for a lot of other. The fact there is a lot of it's really about letting the noise talk and kind of shape it, as if you're kind of sculpting a statue. Which is that's very different from what you get in like a lot of. It's very organic. It just feels it's kind of controlling a process more than actually logically putting step by step. So it feels quite more biological. And I think since there is virtually no one just looking at the conceptual aspects of diffusion. This is something very new, and 99% of people are very engineering-minded people who just want to get better images. So you just have this 1% of people of a decently fringe field at the end of the day. And there is just a lot to discover. There's just a lot to discover, because there is nothing that many people looking into.
The inspiration for you is that neural networks were a fringe field for 30 years. So, and then look where we are.
Yeah.
This is amazing. I'm looking forward to learning more about diffusion now.
If you ever want to write a book about diffusion, just count me as consultant.
I would be happy to. Yes,
I'm sure you can find better ones, but at least I will be. Again, I don't know if the general audience will be interested in this kind of things. So maybe we are still at the stage that is.
That's my
for
job,
experts.
to make it interesting to the general audience. Yeah.
Like I was imagining stuff like, I don't know, like the physics of creativity or the physics of creation, there is something deeply physical about, we actually describe it with kind of with the laws of physics. In fact, one of the papers that we wrote, and also other people, it's really finding like phase transitions in diffusion models. What we can find, we find these events that we call spontaneous symmetry breaking. That, of course, you know the term, right? You have interviewed a lot of physicists, and it's but essentially you have the exact mathematics of a spontaneous symmetry breaking in magnetic materials within a diffusion model, and that corresponds again to creativity. Essentially, spontaneous symmetry breaking happens when the score kind of goes to zero. Again, remember, the score is just a filter. There will be rare situation in which the noise can talk. This paradoxical aspect of diffusion is that a point in time is the most important when your network is doing nothing. Because that's when the bandwidth is maximal. Since the network can only stop the noise, essentially you will get that the highest entropy is when the network is minimally nudging the system. So when the network is very active, the noising is deterministic. Then there is no information be created. So that's it's very counterintuitive. You wouldn't imagine, but it's very straightforward from the math.
I have to understand the math. I don't know enough about it, but this sounds very lovely. I'm going to
It's not
take a
too
look at
difficult.
it.
You can.
Okay.
It's really not too difficult. It's not very advanced. So the main derivation requires some integration by parts and stuff like that, which you could even ignore and take the formulas for granted. For the remaining, there's nothing too sophisticated. Yeah, but it's definitely worth looking into it. It's really pretty.
I will. Yeah, thank
I'm
you.
sorry for getting so much of the attention. When I start talking about diffusion, then I cannot stop talking.
No, this is very exciting. Yeah, no, I'm very happy to talk about this. Thank you.
Okay, well, thank you very much for joining us. I feel I could be here talking for 2 more hours. There are a lot of things I didn't ask, but that's the way it is.
It was a pleasure talking to you, Luca, and Dejan. Thank you. This was wonderful.
Likewise. Thank you very much. Then see you soon.
We'll catch up
Bye-bye.
later. Yeah. Bye.
Thank you.
Hey, Dejan? Dejan, can you hear me?
Yes, just a moment.